All right, so exams tomorrow, it'll be online. If you want to come into the class, we have plenty of spots available. So let me know if you're going to come, just so I make sure I have a printed copy of the exam for you. I think right now we're expecting about 15 or 20 in each class. So we have plenty of space. Just let me know if you're coming so I can send a copy for you. Just remember that if you're coming into the class, I still expect you to have a laptop. You can just log in and then set it off to the side and take it as you normally would, and then put in your answers into Respondus. You have an hour for the exam. It's 28 questions. There's a give me question at the end. I had the equation sheet in the exam, so it's question number 1. So if you can sort of scroll back up and look at it. I will have a paper copy of that for those folks that are coming into the classroom. If you really want a paper copy, you can print it out on your own and just show it when you do your environment check. If that's something that really helps you to have a paper copy of the equation sheet, that's fine. You can print it, just show it to me when you show your scratch paper. It's only chapters 5 and 6. I sent an announcement about that. Chapter 5 and 6. Chapter 5 is on work and energy. There'll be problems where you have to calculate the work and do conceptual questions about the work. Remember, work is equal to FD cosine theta. There will also be some problems where you have to consider the work energy theorem, that if I do work on an object, that changes the energy on the object. And then there will also be questions about the conservation of energy, where the energy initial is equal to the energy final. And then chapter 6 is all about momentum. And those are sort of 2 big classes of problems. That is impulse, or Newton's second law. Remember, impulse by definition is just a change in momentum. But we often consider it when we're talking about force. Force is a rate of change of momentum, or a rate of change of time for momentum. This is really just a recasting of Newton's second law. It's how Newton wrote a second law. And then also conservation of momentum in collisions. We'll work some problems for all of these and look at some of the conceptual questions. But before I sort of launch into that, we can sort of go through some of the old exams and look at questions. Do you have specific areas that you're concerned with, or specific problems that you want me to clarify or work here? Yeah. Okay, yeah, so you'll have, I think there are at least 3 spring questions that I can think of right now. I think they're all calculation problems. And so spring questions, we'll look at some on the old exams. But remember, for springs, that comes up when we're talking about this, conservation of energy. But there are some other things about springs as well. First is Hooke's law. F is equal to negative kx. That is, if I have a spring at x equals 0, the force that it exerts is equal to 0, right? That's its equilibrium position. But then if I have a spring that is compressed a certain amount, so this is x equals 0, this is x equal whatever it is, 10 centimeters, that force is equal to negative kx. One thing to point out with this, and I'll show you in some problems, but just be careful that when you're looking at the direction that the force that the spring is exerting, that direction is opposite the displacement. So in this case, the displacement is in that direction, and the force is in this direction. That's where this negative comes about. So I'll ask you a question, what is the force? What is the magnitude and direction of the force? You can calculate the magnitude in this way. And actually the direction comes out too, but just think about the spring. I can look at this spring and say that it's pushing in this direction. Or if I pull the spring back past the equilibrium position, it's trying to go back here. So that force would be opposite then. You follow what I'm saying with that? That works out with the math if you do your displacement correctly. But I find it's always more useful just to think about the spring. So what is the direction of the force that spring is exerting? The other thing that comes up with springs is elastic potential energy. That elastic potential energy is 1/2 kx squared. If I compress a spring, it gets a certain amount of potential energy, or elastic potential energy in it. And there are 2 types of problems that you can see with these. One is where I have a spring, we've worked this in class before, where I have it compressed, so it has elastic potential energy, and then it stretches out, and this object goes away where now it just has kinetic energy. I'll work one of those in just a second. There's another type of problem where I have an object at a certain height, and it just has potential energy, gravitational potential energy, and then it falls down onto this spring, and all that gravitational potential energy is converted into elastic potential energy. So this object would fall down onto the spring, compressing it. And the way that you would approach that is you would say mgh, that's the gravitational potential energy, is equal to 1/2 kx squared. That would be the elastic potential energy. You're always just converting energy from one type to another. And in that case, you'd be converting from gravitational to elastic potential energy. Okay? Let's look at some of the old exams. I'll pull out some of those. But if you see others that you want to work, you let me know. Mostly in exams 3 on this. I think completely in exams 3. I'm going to go, what was it, 16, 17, and 18? I'll go to 15. So we'll just get a little variety. Okay, number 7 is a good example of a conservation of energy problem with a spring. So I have a 10-kilogram car that's moving at 5 meters per second, and it hits an uncompressed horizontal spring. That means that initially I only have kinetic energy in my system, and then it compresses that spring, and all that energy is going into elastic potential energy. So I'd say 1/2 mv squared is equal to 1/2 kx squared. And I know everything here. I'm looking, though, for the compression of the spring. I cancel out these halves. The mass is 10. V is 5 meters per second squared. That's equal to 250 x squared. And then I'd solve that for x. That is 200, well, x would be equal to 1 meter. Because this is 250, this is 250, this divide through x would be the square root of 1. Okay? That's one type of problem. I'm pretty sure that you'll see that. I think I remember putting that in there. Can I clear this? Okay, this is a similar problem. You'll see this where you'll have series of problems that follow after one another. This one's just asking what is the potential energy of the spring, in which case I already know that x is equal to 1 meter. That is, it compresses it by 1 meter. And so I could say just 1/2 kx squared is the total energy in that spring. That's 1/2 of 250. That's the spring constant times 1 meter squared. So it's going to be 125 or 130 joules. Notice I also could have done 1/2 mv squared, because I know that's also the total energy. That's 1/2 of 10 kilograms times the speed, which is 5 meters per second squared. That's 5 times 25 is 125 or 130 joules. So either one of those ways would be appropriate to answer that question. Number 9 is the other type of question that you'll have, where I ask you how much is the spring compressed, and the spring is compressed. F, I know, is equal to minus kx. So I have a force of 600 newtons. The spring constant is 1,200 newtons. And I want to know what x is. 600 divided by 1,200, that's 6 over 12, or 0.5 meters. This is just looking for the magnitude of that displacement. You see, none of the options have negatives or positives. I'm just looking for the magnitude. That might be the case, but I might also have positives and negatives. I'll make that very clear in the problem. Just think about, what is the direction that the spring is pushing. In this case, well, I don't give you any direction, so you don't really have any way of deciding is that positive or negative. Those are sort of the spring problems that you'll see on the test. I don't think there are any conceptual questions. I'm pretty sure they were just sort of like this. Hooke's law, elastic potential energy, and the conservation of energy. Converting either from potential, gravitational potential to elastic potential, or kinetic energy to elastic potential energy, or vice versa, the opposite direction. Okay? Maybe some Clarity on those? Yeah, you're going to see several of those. So, don't miss them. That's a letter grade. 3 or 4 questions is a letter grade. Can I clear this? Get them all right. That's what I really want. I really want you all to get every question right. Like, it would just make my day. It make me so happy if everybody got every question right. You want to do other energy problems or other conceptual questions? You'll have questions like number 1 and 2, or excuse me, number 2. In fact, you'll have several questions that are a roller coaster type problem. We can take a look at that. Oh, okay, take a look at that. So on those, you really want to, yeah, Cameron. Thank you. Yeah. Huh? I'm about to do number 2. That's a good idea. So on number 2, this is fall 16, 15? What was this? Yeah, fall 15, number 2. This is problems number 1, 2, and 3 on the exam. And the first thing that I ask you is, what type of energy does this object have at a particular point? So let's just take this problem. Your problem will be different. But at point A, what type of energy does this object have? Well, I know it has potential energy because H is not 0. And then the question is, does it have kinetic energy? Does this one have kinetic energy? It does, because it has a speed. If it were at rest, no kinetic energy. But this one has both potential and kinetic. At this point, and then I want to know what is the speed of the card at point B. Potential energy at point B? No, because H is equal to 0, so it only has kinetic energy. So I'll ask you that question first. That's question number 1. What type of energy does this object have at point A, B, C, D, or E? Okay? You're going to get that one right? And then that sets a good tone for the rest of the exam. Question number 2 is, what is the speed or what is the height at this other position? In this case, it's asking what is the speed at point B. So I would say mgh plus 1/2 mv squared, that's at point A, is equal to mgh at point B. If you want to do subscripts, you can. But I'm just going to put in some numbers here. I'm going to get rid of my m's, by the way. So 10 times 10, that's g times this height, plus 1/2 of 4 squared, that's this speed, is equal to 10 times, oh, I'm sorry, I made a mistake. Because my height there is actually 0. I'll just scratch there. 1/2 v squared. So this should be 1/2 v squared. 1/2 of v squared. So that's 100 plus 8 times 2 equals v squared. It's the square root of 216. Is it 16? No, 15. 15 meters per second is the right answer there. Okay? That's question number 2. And then there's a similar question where I ask you at some other point, what is the speed or what is the height? So for example, if I'm asking the height at point E, where the object would come to rest at point E, you do this very similarly, where you'd say the potential energy plus the kinetic energy at point A is equal to just what type of energy at point E? What does it have up here? Just potential. So I've set this equal to mgh at point E. These are questions 1, 2, and 3 on the test. All right, what's question 4? Do you know what question 4 is? I think you have questions like number 5. By what factor does the kinetic energy of a car change if its velocity is doubled? Somebody was asking about, that's what this chicken scratch is about up here on the board. So if you get something like this, just remember, or look on your equation sheet, the equation for kinetic energy. By what factor does the kinetic energy of a car change if its velocity is doubled? If I double this variable, because it's squared, that means I'm going to quadruple that variable. Okay? Those are important questions, not just for this class, although it is important for you to understand the relationship between variables, but for other tests, standardized exams and the like, that sort of thinking about variables in that way is important. Also, make sure that you know what conservative forces are. Conservative forces conserve energy. All right, that's why they're called conservative, because they conserve energy. And only field forces conserve energy. Because field forces act over a distance, the two objects don't have to touch. Anytime objects touch, they lose energy because they're interacting with one another in a certain way. Also, conservative forces are path dependent. That means, oh, I'm sorry. Conservative forces are path independent. Non-conservative forces are path dependent. I talked about this in the video, but we didn't get into this in the class really. But if I have, say, two paths, let's say that I'm going up a mountain, and I have two paths. I can go one path that's all windy like this, and I can go another path that goes straight up like that. Now, my potential energy has changed the same for both of those because the potential energy deals with a conservative force that conserves energy. But if I think about friction, I lose more energy in the red or the black path. Friction is a non-conservative force. It doesn't conserve energy. It loses energy. And in which path do I lose the most energy? The black, because it's a longer path, and I just have more time to lose that energy. In fact, the energy that I lose due to friction would be equal to the frictional force times the distance over which it's applied. That's the work energy theorem, and you'll see a question like that where I have an object that has a certain amount of energy, and then it moves over a certain distance with a frictional force, and then what is its new speed, or how far does it move? You've seen problems like that. We'll look and see if we can find one here. Okay? Clear this? I know it's fast. Y'all stop me if I'm going too fast or if you're just lost. That's okay. Okay. I want to go back. Let's go back to another exam. I want to find an example of that I was telling you. This is at fall 17. Okay, fall 17. This is number 2, where I asked how fast is the kid going when he reaches the bottom. We worked this in one of our sections. I forget which one. But if I have this slide where a kid is initially at rest, but he has potential energy, at the bottom, he has kinetic energy. All that potential energy is converted into kinetic energy. But along the way, he's losing energy due to the frictional force. And that frictional force is 5 newtons over the distance, which is 4 meters. So he is losing 20 joules of energy as he goes from the top to the bottom. And I want to know how fast is he going when he reaches the bottom. The way I can think about this is my potential energy minus the work will be equal to the kinetic energy at the bottom. Potential energy at the top, kinetic energy at the bottom, and then this work is the work that's done by friction on the kid. So I know the potential energy here is mgh. That's 10 kilograms times 10 meters per second squared times h, which is 2, minus the 20 joules due to the frictional force is equal to 1/2 of 10 times v squared. That frictional force takes energy away from the kid as he comes down. It slows him down. Now I can solve this for v. It's 200, that's 180 divided by 5. What's that? What's the answer? 6? Okay. All right, yeah, so v is 6. Yeah, right. Okay? You're going to see a similar question to that applies both conservation of energy and then how does friction come into play where it begins to take energy away from that object. Expect 1 or 2 questions about that. Courtney?
I think I got like a very similar problem somewhere on one of the texts, but the mass of like the child wasn't given.
Yeah.
So you had to do like I don't remember how to solve it like currently.
Yeah. Was it in one of the exams we had in the workbook?
I don't remember.
You're not helping me very much.
Yeah, 14 and 19. That's not very helpful.
Not helpful at all.
could it like as newtons and you'd have to like divide by 10?
Oh yeah, so
Yeah.
be careful in that. I think that actually happens tomorrow. If that's what you're saying, that I don't give the kids mass, I give the kids weight.
Yeah.
I don't think that's what you're saying, but
I don't remember exactly what it was.
let me address that. So just be careful because there is a question where it gives the weight of an object, like I don't know, a 700 Newton kid. That's a pretty big kid. A 700 Newton kid, and then if you need its mass, don't forget that the mass is equal to 70 kilograms, because mass is F over G. And so if I give you the weight of the object, which I sometimes do because I'm a jerk and all that. But if I give you the weight of the object, then you just divide by 10 to get its mass. Don't let that trip you up, okay? Watch the units. Units are always a good indicator of what you're working with. And that does happen tomorrow. I do give you the weight. Okay? Where you really need the mass. And if you don't use the mass, you get an answer that what? Is going to be an option? Of course, right. Because every mistake that you can make to try to, anticipate your mistakes.
It's fall 19.
You're amazing. Fall 19. All right. Yeah. So this is a good one too. This one's similar. I have a cardboard box that has a speed of 6 meters per second. And then it slides along, and I want to know how far does it slide before it comes to rest. So what's happening here is this object has kinetic energy. And then all that kinetic energy is taken away as it slides through that distance. So 1/2 mv squared, that's its kinetic energy, will be equal to the work done by friction, which is going to be F times D. That's the framework that we're starting with. This is the work energy theorem. My work causes a change in energy. The work done by frictional forces is changing the kinetic energy. So you're right, I don't give you the mass. However, I know that friction is equal to mu times the normal force, and that's equal to mu times m times g. That's not on your equation sheet, but that's something you still need to know. You understand? You still need to know that your frictional force is proportional to Fn and mu. Then 1/2 mv squared mu m g d. Fortunately, our masses cancel out, and then I can solve for d. So I'll just put some numbers in here. 1/2 of 6 squared is 36 equals 0.2. 10 d. It's 18 divided by 5. What was the answer? 3.5? I think it's 3.5. Is that right?
9.
9? All right, hold on. This is 18 equals to 5d.
Why is it 5? I would say 2.
Oh, yeah. Right. 18 divided by 2, so d is 9. You're right. 9 meters. Sorry, it's been a long day. Hopefully you have a not long day tomorrow and get lots of sleep tonight, okay? Do not stay up all night. That doesn't help anybody, okay? All right. Good questions. Those are great. Good examples of what you'll see tomorrow. Everything that I've done so far, I think, is on the exam. Do some momentum problems. That's about half the exam. This is fall 17. Number 12 is dealing with this idea that F is the time rate change of momentum. The rate of change in time for momentum is our force. And so I give you the impulse, that's delta P right there is equal to 20. And I give you the time right here, delta t. So a lot of these problems are really just being able to pick out what the variables are. That's not always easy, especially if you're not familiar with them, but that's the skill that you need to build. And so our force is equal to delta P over delta T. That's going to be 20 divided by the time, which is 4 or 5 newtons. Likewise here, some conceptual questions that you'll probably see. So when does the net force on an object increase? Well, the net force can be increased by either making this smaller or this bigger. Right? If I make the denominator smaller, F gets bigger. So that's the answer, actually. If I make delta P smaller for A, that doesn't make F bigger. And if I make the denominator bigger, that doesn't make F bigger either. That actually makes it smaller. Number 15 is a conservation of momentum problem. You'll see a couple like this. I'll give you one of the problems like number 14, which we'll show you in just a second. But where I give you a figure, I think those, you sort of get to the routine of those. You probably go through this pretty quickly. But number 15, you really need to think about, make sure that you're getting all the picture in your mind correct. And so you'll see something like this tomorrow. A person with a mass of 60 kilograms throws an object with a mass of 12 kilograms. So this is my image. I have a person and they have an object. Initially, they have 0 momentum because they're just standing there. And then the person throws it away in one direction, and so the person goes in the opposite direction. So in the next situation, this ball goes in one direction, and the person goes in the opposite direction. Mathematically, how that would look would be 0, that's the initial momentum, is equal to the person who has a mass of 60 kilograms, and we're told they have a velocity, the person has a velocity of 2 meters per second, plus the mass of the object, which is 12 kilograms, times its velocity. And so that velocity is 120 divided by 12, or negative 10 meters per second. Be careful here, because you might have said it was 10 meters per second. But if you work this out, it will work out to be negative 10. But then also I know that my velocity of the person is positive 2. I actually drew this picture wrong, right? That I should have flipped it the other direction. But the velocity is positive 2, so the velocity of the ball is going to be opposite that. Because I know I have to equal an opposite momentum. That's a conservation of momentum problem. You could see a problem, you will see a problem, like number 16 as well, where I'm not changing, I'm not ejecting something, I'm actually changing the mass. And if I change the mass of an object, that also causes the momentum to change, or rather, it doesn't change the momentum, but it will cause the speed to change in response. So if a cart has a mass of 20 kilograms, and is traveling to the right at 12 meters per second, that's the initial. And so my momentum in this case is equal to 12 times 20, or 240. But then if I increase the mass of the cart, I drop something into it. So now it has a mass of 30 kilograms, and I want to know what is the velocity equal to. Well, the velocity is still, or the momentum will still be 240. So I say 240 is equal to 30 kilograms times my new velocity, or 8 meters per second. So you see it slows down. It was going 12 meters per second, but now it's going 8 meters per second. You'll see a problem very, very similar to that. Everything that's on these exams, you'll see tomorrow. That's why they're good practice for you, but they're different too. So don't just memorize them. That won't help very much. But know how to work through the problems and know how to think about the concepts. Okay? Let's see what else we got. We can come back later if you want to work through this, but I think most people are good with problems like number 14. Yeah, Megan? Sure. Yeah, so this was kind of like the problem we were talking about earlier. Great problem. How does the work required to stretch a spring 6 centimeters compare with the work required to stretch it 2 centimeters? And you might say, well, we haven't really talked about the work required to stretch a spring, but I do know that any work that I do on an object will change, excuse me, will change its energy. And so all I need to know is how much energy does a 6 centimeter spring have more than a 2 centimeter stretched spring? Well, this is 3 times as much, right? This is 3 times the x elongation, and x is 3 times as much. I know that potential energy for a spring is 1/2 kx squared. If I triple x, that means my potential energy is 9 times. That means it requires 9 times as much work to change to stretch a spring 6 centimeters than it does to stretch it 2 centimeters. Just knowing you don't have to know your equations, right? Because I give you the equations. A lot of things you probably do know them by now, aren't that many. But being able to analyze them in that way is a really important skill, not just for this class, but just, life. Okay? Good question. We'll see something like that tomorrow. All right. Any other specific questions as we move along? On this exam?
Yes.
Okay. So the important thing here is that the inclined plane is frictionless. So if it's frictionless, the change in potential energy will be the same for all of these. This is frictionless. So the change in potential energy is the same. Now follow me? There's no energy lost. None of these blocks lose energy as they move from here up to here. They're all moving through the same height. And since they're all moving through the same height, then these forces, which are the forces that are moving them up, will all do the same amount of work. Because my work, any work that's done by these forces, is resulting in a change in potential energy. And so the 3 forces here will do all the same work. What if there was friction? Which force would do the most work? C, very, very good. C would do the most work because it's losing the most energy from friction. It's going to have to actually be a bigger force. Well, I don't say it's a bigger force. It does more work because it has to counterbalance the frictional, the energy that's taken away from friction. That's a good question. So let me just repeat that. These objects are changing potential energy as they move from here up to here. They change potential energy by the same amount, the gravitational potential energy. If there's no friction, there's nothing taking energy away. And so each of these forces, even though they're all different, will still do the same amount of work. Right? This is a bigger force, but it's acting over a shorter distance. This is a smaller force, but acting over a bigger distance. They do all the same amount of work because there's no friction. But if I have friction in there, friction, which is a non-conservative force, it does not conserve energy, it's taking energy away from those objects as they move up the inclined plane. Because this one has a longer path, that friction is taking away more energy. And so this force, which still has to produce the same change in potential energy, will have to do more work to move this object up because of that frictional force. You might not see a problem just like that, but you definitely have inclined plane problems where I ask you questions about that are similar. Okay? All right. Go on. Good question. What else do you want to look at? Don't forget that the concept tests, which are on Moodle, you see a lot of those questions in the old exams, but those are also great practice for you. Like I said in class, print them out 6 to a page if you like to print, or you can just slide through them on your phone and just quiz yourself on those, and you can read the explanations as well. Okay? What else? What are your weakest points? Your fun. Yeah. Which one? Number one? Yeah. Okay, so this is like the roller coaster problem. It just looks a little bit different. I have a bug right here, and then it slides down the bowl, and I want to know what is the speed down here. So I need to ask myself, what kind of energy does this bug have at different points within this, situation? Up here, he has a speed and a height, so he has both kinetic and potential energy. But down here, he only has potential energy. So I'd say 1/2 mv squared plus mgh equals mgh. I'm sorry. I did that again, didn't I? Sorry. He only has kinetic energy at the bottom, so it's equal to 1/2 mv squared. That's right, huh? That's correct? Okay, good. All right, so I can cancel out my masses. Those all go away. I'm looking for his speed at the bottom of the bowl. So I have 1/2 of 1 squared, that's my speed here, plus 10 times 0.4 equals 1/2 of v squared. That's 0.5 plus 4 times 2 square root is equal to 3. So B is the right answer. All right? Other questions? I'll sort of scroll through some of these. And you'll holler out conservative forces, non-conservative forces. Make sure you know your units. There's at least one question about units for work, energy, time. Just look at, just look at the equation. So this actually isn't units. This is just the definition of power. Power is work over time or energy over time. But if I ask you the units for, say, energy, then you would say, well, I know energy is 1/2 mv squared. So that's going to be kilogram meters per second squared. So it's kilogram meters squared per second squared. Or if I ask you the units for momentum, that's mass times velocity. That's kilogram meters per second. Or if I ask you the units for power, that's energy over time. So it would be this and then over time. So it would be kilogram meters squared per second cubed. Don't try to memorize all those units. You're just going to fill up your brain. But make sure that you can go through and look at the equation and remember the basic SI units for the mass, the length, the time. Put those in, and then you can get the units for those. Those should be Guinea questions. I want them to be Guinea questions. Should get those right. There's at least one or two that are dealing with units or something like this, and knowing the definition of power or work or energy. We've done a lot of these. And you'll have a collision problem like this. Make sure you get the signs right. So this would be 1 times 3 plus 2 times -4 equals 1 times -1 plus 2 times VF. Just make sure you're getting the signs right. Your work will probably look very similar to this as you go through, making sure that this velocity is negative, this velocity is negative, and then solving properly for VF.
Could you do number 10 on call 15?
Sure. Okay, so in this one, I have a railroad car, and I have a gun that's shooting bullets in this direction. And those bullets have a mass of 0.025 kilograms, and they have a speed of 250 meters per second. And I want to know how many of those bullets do I have to shoot off in order to give my railroad flat car a speed of 0.5 meter per second. This is a momentum problem. It seems more complicated because now I have these multiple objects that are coming off, but it's really working the same way with just one small change. I have the momentum of the railroad car. That's going to be 6.25 times 10 to the 4 kilograms times 0.5 meters per second. And then that's going to equal to the momentum of the bullet, which is 0.025 kilograms times 250 meters per second. But I don't just have one bullet, I have a bunch of bullets. So I'm going to just multiply that times n. This would be just like if I had, each bullet has the same momentum, so I could say this plus this, however many times I needed it. But I'm just going to multiply it times an integer n, or it will be an integer. So if I want to know how many bullets that is, I'll solve that. 625. I get n is equal to 5,000. So you have to shoot 5,000 bullets in order to get that railroad flat car a 0.5 meter per second. I mean, you're going to see conservation momentum, but I didn't have any questions like that. I mean, sometimes in my classes, like we'll have a particular question in class or in a homework or something or whatever that I put that, but we didn't really do anything like that. Okay? But the idea is still the same for conservation momentum. All right. Momentum. And remember, no past 20 here. There's no rotation. Anything else? Sure.
Yeah, for the concept test, 5.8 for mass accelerates to 30, like which takes more energy.
Oh, yeah. Sure. Yeah, this comes up in some of the old exams. So the question is, which takes more energy? For a car to go from 0 to 30 miles per hour? Or for a car to go from 30 to 60 miles per hour? That's in the concept test, but it's in the old test too. I don't know where it is exactly. What's relevant here is the amount of energy to go at these speeds. And I know that my kinetic energy is equal to 1/2 mv squared. So if I were to plot kinetic energy versus v, it would look like that. And so if I'm going from, say, 0 to 30 miles an hour, I just need this much energy. But if I go from 30 to 60 miles an hour, I need this much energy. So it requires a lot more fuel, a lot more energy to travel at those faster speeds. Of course, cars today, they're optimized for a certain speed. Not 75 or 80 or 90 or whatever it is y'all drive, but more like 45 to 50 miles an hour. That's sort of your sweet spot for getting good gas mileage.
I guess I had in my head that you have friction and then it takes more work to overcome to start from nothing to 30.
That's true.
Momentum.
No, you're right. But this relationship is so overwhelming that it takes a lot more energy to travel at higher speeds. My dad was like the slowest driver in the world. He was driving me crazy because he would pull over every like 5 or 10 minutes to let the 50 cars that were behind him just go on by. But he would travel so slowly. But he got good gas mileage, and he drove his car for like 600,000 miles or something crazy. He's still around. Like he sold it to somebody for like $100. And they still drive it around. He was a mechanic, so he took good care of it. But, okay. But he is, but he's still alive, thankfully. All right. Anything else, y'all? You feel prepared? Feel ready? I've been saying this is the easiest exam. That might be true, but exams 1 and 2 were not easy. So if that's your standard, then I wouldn't say that it's easy. It's easier than those exams. So like I said, don't not study. You need to prepare for it. Okay. All right. Just check in, make sure I got you before you leave.